All right, so the last thing we're going to talk about tonight are partial derivatives, and I'm going to let you off the hook. Well, I'll be honest. I'm going to let myself off the hook and not get into the limit definition of a partial derivative, because really, it's the same as the limit definition of a derivative. You're just going to have y's in there when you're taking the derivative with respect to x, and the other way around when you're taking the derivative with respect to y. It's really just kind of aggravating. Especially since it's something that you would already have a pretty decent sense of. Now we will get into the graphical representation of this stuff because there is a lot of meaning to it, because we're taking a partial derivative. So what is that, like a quarter of a derivative? What are we talking about here? Is it like a little piece of a derivative? What's going on? You know, so we do have to get into like why on earth would this be a useful thing to learn about. But for now, you know, with the last few minutes that we have, we're just going to get into the act of taking derivatives, and also what are known as second order partials. All right, the notation, it looks pretty similar to the ordinary notation for derivatives. It's just the lowercase delta symbol is actually what we use for partial derivatives. Okay? Now, it's kind of interesting to think about this, but I don't know if you ever got the origin story behind the notation in Calc 1. When you learned about dy dx, and I'll just actually do that real quick, because I think it's valuable for people to know this, because some of the notation seems like it comes out of thin air, but it really doesn't. So you have slope, general slope formula, delta y over delta x, right? That's capital delta. And I'll highlight it. Got to move slightly and then highlight it for some reason. All right. Now, that slope is specifically over an interval. All right. So slope over an interval. I always felt calculus as being an entire set of course. Well, it depends on the course, but Calc 1, I say it's an entire course dedicated to the study of slope. And I don't think I'm lying. I think that's actually what it is. All right? It's just what are you doing with those slopes. Then you have slope at a point. All right? And so for that, we use delta y over delta x. All right? Also delta, but this time it's a lowercase delta. All right? So what happened is in Calc 1, they kind of streamlined that down to just d, with the reason being, I'm not going to write that symbol over and over again. That seems like a waste of effort. So we'll just use d. The reality is, even in Calc 1, you were working with partial derivatives, because every first single variable, I almost said first order function, single variable function can also be thought of as a multivariable function, but with one of the variables being held constant. All right, so when you're taking the derivative of y in terms of x, you are taking the partial derivative of the function y in terms of x. It's just you're holding y constant.
Does that mean we can just use d here? Oh, lowercase d.
Well, that's the thing. Moving forward, we're going to use lowercase d for something else.
Oh.
So, you know, basically what I'm getting at here is that in Calc, all the way through now, we have been using dy dx incorrectly, because it means something completely different.
So it should have been this symbol the whole time?
It should have been this symbol the whole time.
Oh.
So, but, you know, like let's say you never get to this course, what do you know? What do you care, you know? So, but it isn't until this moment where it becomes relevant. All right, so when I say delta f delta x, I'm saying the partial derivative of f with respect to x. All right, because what I could be doing is taking the partial derivative of f with respect to the other variable in the function y. I could also be taking the partial derivative of f with respect to some constant. You know, that's the thing. Like, what you're taking the derivative with respect to, it could be anything. sometimes not even relevant to the function. Like for example, I have a function here in terms of x and y. I could take the derivative of this with respect to t. And we've done that before. That's parametrics, right? We could parameterize it in terms of a new variable, right? So there's no limit to in what way you can differentiate. Because really, if you go back to the idea that slope is a rate of change, you could create a new rate of change. I mean, I could take the rate of change of your grade over time, right? I just take like what the change is over the number of days, right? Or does it make sense? I don't know, right? Maybe you want to divide it by the number of tests. Like if I want, like let's say you have 3 tests, all equally weighted. You could average them together, all right? That average is a rate, right? You're taking the rate of change of your test scores per unit of tests, all right? That's what a mean is, that's what an average is. But then I could take that rate and relate it to time and create what we called in Calc 1 related rates, all right? So I could differentiate with respect to whatever I want. So this notation is the all-encompassing notation that we use for any kind of derivative, no matter what the variable is, right? And we'll talk about next class what the lowercase d actually means, right? But all this is telling us to do is treat y as constant and differentiate with respect to x, all right? So we're going to treat y as constant. All right, there's multiple forms of partial derivatives. The 2 most popular are this one and also the lowercase f with a little subscript of x. That means the same thing. People like this one, I think for obvious reasons. It's less writing, right? So just f with a little subscript of x. And then when you get into second order partials, which I should have, yeah. So here's a second order partial. For example, this is a mixed second order partial. First derivative with respect to x, second derivative with respect to y. You could write it like that, but if you use this notation, it's much simpler. All right, so we'll get to that in a minute. So, yeah, partial with respect to x. We do it a piece at a time. I'll color code. One thing I think that you'll probably like about this is that it takes functions that look like it's probably supposed to be product rule or quotient rule and makes it much simpler. All right, so 3x squared, my variable is x. So that's just, I take the derivative of that the way I normally would. So 6x. 4y squared.
Is that an F or a Y?
Is that an F?
Delta.
Oh, delta F. Yeah, it's supposed to be an F. Poor quality F. Because what's happening is when I take a derivative, or actually if I just have a function defined in terms of x and y, it's implied that that function represents z. You know, f of x was the same as y. F of x comma y is the same as z. Right? So this is really, I mean, if you were to use prime notation, you would think of this the way you would like y prime. This would be like z prime. Right? But z prime of what? Like, are we talking in terms of x or in terms of y? So we have to be more particular about our notation here. All right. Now, 4y squared. If we're treating y as constant, then 4y squared itself is constant. Derivative of a constant is equal to 0. That just got a whole lot nicer. This next piece, you don't have to do this step of rewriting it, but at least this one time, maybe you should. I'm going to rewrite it as negative 2y times x squared. All right, because y is constant, that makes the negative 2y into a constant multiple. scalar multiple. So when we take the derivative using the power rule, we take the power, multiply it by the coefficient, reduce the power by 1. That y, I mean negative 2y, that might as well be negative 27. Or negative 200 if y was equal to 10. Whatever, it doesn't matter. You're treating it like you would if it were a coefficient. So 2 times negative 2y is going to be negative 4y. Reduce the power of x by 1. So times x to the first power. Do the same thing for the next piece. 7xy squared. We could think of that as 7y squared times x. That x has an understood power to of 1. Power multiplied by coefficient. Because again, that's 7y squared. No matter how complicated it is, it only consists of coefficients multiplied by y's, which we're treating as constant. So no matter how complicated it is, it's still going to be treated as a constant. All right, so 1 times 7y squared is 7y squared times x to the 0th power, which would go to 1 anyway. And that last little negative 9 there, irrelevant, because the derivative of a standalone constant is going to be 0 anyway. So we're looking at 6x minus 4xy plus 7y squared. All right. Now, in Calc 1, the way you would have handled that, you would have had to use implicit differentiation and product rule. That would have been crazy. Mechanically, this is not bad. All right? It's just not something that you're overly eager to do, but it could be a lot worse. Oh, speaking of worse. Compute all 4 second-order partial derivatives. All right. So what I'm going to do is snag my previous answer. So partial with respect to x was 6x minus, what was it, 4, was it 4xy plus 7y squared. All right. It's when you get into second order partials where you're like, yeah, let's talk about that other notation right quick. So we could look at this as just an f sub x. Because if I want the second order partial, fxx, fxy, we need them both. All right, because all 4 would be partial with respect to x, then y, x, then x, y, then x, and y, then y. All right, so we have all those permutations that we have to account for. All right. And you can do it in any order you want. I tend to want to do the mixed because they're actually, I'm going to steal my own thunder a little bit. There is a relationship between mixed higher order partial derivatives. So if your function is continuous, then your mixed partials will be equivalent, right? So your f of x y would be the same as f of x, f of y x, right? So, but that's only if it's continuous, which is why we were talking about continuity, right? So you just have to keep in mind what it is you're looking for here. So I'm working off of my first order partial with respect to x. Now I'm going to take its derivative with respect to y. All right, so my variable here is y. So I'm going to highlight the relevant variable. Everything else is treated as constant. So the derivative of 6x goes to 0, irrelevant. The derivative of this, that y, has an understood exponent of 1. That is, again, a highlighter and not a marker. Power multiplied by coefficient. My coefficient now is negative 4x. So 1 times negative 4x is negative 4x. Y to the 0th power. Okay, well, y to the 0th is 1, so ignore it. This, I'm taking the derivative. Again, my relevant variable is y, so I'm taking the derivative of this with respect to y. So I'm going back to Calc 1 and taking this derivative. All right, so 14y. All right. Going back to my first order partial, I take the derivative now with respect to x. So 6x goes to 6. That's easy enough. All right, my relevant variables are the x's. That 7y squared is going away because there are no x's in there. So 7y squared is constant. So now it's really just a matter of accounting for this middle one, which could be thought of. All right, so I'll just circle it, pull it off on the side. That's the same as saying negative 4y times x to the first. All right, so power multiplied by coefficient minus 4y. X to the 0th power, drop it because x to the 0th power is equal to 1. All right, so now we got to do all that again, but this time we're starting off with a first order partial with respect to y. Skill-wise, it's going to be exactly the same, though.
Question. Don't we have to do a f of yx? Or we just come to that?
Yeah, that's what we're going to do in a minute, yeah. All right, so now what we're looking at is going back to the original function and differentiating that with respect to y. So my relevant variable is y. Every instance of x is going to be considered constant. So 3y squared, done. I'm sorry, 3x squared. All right, that's constant. Derivative of a constant is equal to 0. 4y squared, take the derivative of that Calc 1 style, 8y. This could be thought of as negative 2x squared y to the first power. Power by coefficient, reduce the power by 1, negative 2x squared. Same idea for the next one, except the power is 2. So plus 14xy. So now I want to do, I personally, again, like to do my mixed second order partials. All right, because these functions are continuous. I know they're continuous because I don't have any radicals. I don't have any denominators with variables in it. I don't have natural logs. I don't have trig functions. I don't have anything that would cause any funky values here. So I expect this mixed second order partial to be the same as that one. All right. So I'm differentiating with respect to x, which means that the 8y is constant, goes away. This one becomes negative 4x. And if I think of this as 14yx, that would differentiate down to 14y. All right, so it verifies what I was saying. I mean, maybe not the continuity part of it, but at least that the second order partials would be the same. So, you know, you kind of look at a situation where maybe you have a fourth order partial that has 2 x's and 2 y's in it. It doesn't matter what the arrangement is. All right, so let's say it's a fourth order partial. So the fourth derivative, and in one case it says you're supposed to do f sub xy xy, and in another case it says f sub yy xx. All right, they're both mixed fourth order partials because the functions, I'm establishing that the original functions are continuous. Those two mixed fourth order partials should be equivalent to one another, which means pick the easiest pathway to get you to that arrangement of partials and you're good to go. All right. For here we go back to f sub y. So 8y becomes 8. We don't expect this to be the same as f sub xx, so all bets are off here. But nicely, the negative 2x squared is going to go away. And we'll be just looking at 14x. All right, so plus 14x. All right. So numbers 3 and 4 are basically a rehash of 1 and 2, except there's some trig and exponentials in there. So again, my teacherly right.
This is compute all 4 second order, and we got 6 of it.
1, 2, 3, 4. These are first order partials. But we needed to get the first order partials in order to get the second order partials. So, yeah. So there's a lot of writing, and these will take you a few minutes, but it's definitely worth your time because there is a little bit of quirkiness when it comes to transcendental functions, the exponentials and trig, that is worth spending some time on it. All right. So that'll do it. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on Wednesday.
Yeah, I did see my average.
Right.
I was surprised.
Yeah, so I mean, you're in the
Yeah.
game, you know, that's the whole thing.
So, yeah, I just gotta hit the two exams.
Right, and let's see, like you could do some typos, that'll get you up a little bit more.
But yeah, I've always been doing those.
Yeah, you've been doing a
bonus
tech
stuff.
assignment, so yeah, it's gonna just cut it, like if we can get that average up
Yeah.
a little bit.
Okay.
Yeah, you're gonna, like,
Exactly.
it's
So
still
the next-
doable, yeah.
'cause we have another test in the final, right?
Yeah,
Okay, cool.
Do I have hope?
yeah, absolutely. Yeah, because what are we at here? Like,
Probably bad on the phone. I was thinking of dropping this because not that I need it, but I just want to read it. I know
yeah,
I'm trying to do the
yours
homework.
are it's the tech assignments.
Yeah.
If you get, let me just
I
put
have
it
the
in.
time. I work in Jersey City, but I don't want to drive back.
Right,
It's like,
but,
and then I come here. It's like I'm drained. You know?
no, I
I'll do
understand.
them. I'll do them.
Yeah, but let me just put it in perspective for you. If you get those in, you have like a B.
Oh, good.
Yeah, so I mean, it's very doable. Like, you know,
I wanted to get it higher, but it's like
right, but
I
that's
understand
that's
the
a place to
topic.
start, you know?
I understand the topic, but it's memory that's like
Yeah,
it's hard for me to unless I write down every sheet of paper. Then in one, I can't.
right.
Thanks.
Yeah, no problem.
I thought, weren't we supposed to have a quiz today?
Yeah, we were, but I forgot to make photocopies, so that ended up not happening. So I'm gonna reschedule that for next week.
Okay, cool.
So, but I'll talk about it on Wednesday, and then we'll do it next week.
Okay, that's right. I just was wondering about that. And
Yeah.
For the last quiz, for the bonus.
But it was a smart move not to bring it up like an hour ago. Yeah.
I just want to keep my mouth shut there.
Yeah.
For the last quiz, for the bonus, is it still possible if I may hand that in?
The last, the unit circle one?
Yeah.
Let me
get your time under, what, 2 minutes?
Oh, I said that to you.
2:30.
2:30.
Yeah,
Yeah.
that's fine. Yeah, totally.
Where would
Yeah,
that
just-
show though?
What's that?
Where would that extra credit show?
It would be on Blackboard. It's under bonus unit circle game.
Okay.
Yeah, it's all up there.
Do you count this?
And yeah, you got credit for that.
Me?
Yeah.
Alright, because I remember sending it to you.
Yeah, you definitely got credit for that.
Would you count this as an error?
Did you back the test or?
Oh yeah, yours is like right there somewhere.
Oh.
There it is.
I know just like.
Yeah, I didn't so hot.
That, between the F and the parentheses right there, could there be a space?
Yeah. I'll take anything that makes my notes better. Yeah, like I'm not picky. Like even if it's something like aesthetic, you know, like if it'll make it look nicer, if a suggestion, you know, I'll take anything. No problem.
I didn't do so hot on this one.
Yeah. So,
Yeah.
but your average is not terrible. So I mean,
Yeah.
even with that, to still be like living in the B territory is not like.
Yeah. But this one, if this is my lowest grade, this
Then
fits-
it would drop. Just watch attendance because you've been coming in late.
Actually, no, I don't really come in late. I usually come in on time. I usually come in like 5
You're
minutes
half
late.
an hour
All right,
late
that's
today.
that's just for today. I usually come in on time.
I got you 3 consecutive classes late.
Can I see how late was I? Because I remember you saying that I could come at least like 5 minutes late or 2 minutes, and I don't come that late. I know that for a fact. I don't do that.
Yeah, the problem is I wait before I take attendance. So if
That's
you're,
why I was shocked when I saw my participation as 5 out of 10.
yeah. So just like just get that.
Because I know I come in on time. Like I come in within 2 minutes. Within like usually I come on exactly on time. But like I was so shocked when I saw that too because I know I come in on time. Like I don't come in that late. I know you gave me like there's like a 10-minute span or a 5-minute span,
Right.
and I always come in within that. Exception.
That's not the final grade for participation. So like if you could just maybe a minute earlier, 2 minutes. I mean today is a different story, but
Yeah, today was I had supposed to do.
but like yeah, just a smidge earlier.
Yeah.
That'll be fine because that could easily. I mean, it goes. I revised that grade at the end of the
Oh,
semester.
really? Okay.
Yeah, it's not like that grade is the grade and then I
Yeah.
put a new one in. I changed that grade at the end of the semester.
Okay.
So you could expect, as long as you get the attendance squared away, then you could expect that to go up. It could even become a perfect score.
Okay. And I can still apply for my lowest test grade to be dropped, right?
Yeah.
It's
That's why I always tell people to be mindful of attendance because if you go over that threshold, then you lose the ability to drop your lowest test grade, and that's more than participation score. That's the big deal.
Yeah. I don't want to lose that at all.
Yeah.
This test was like, I don't know. I wish I was ready more.
How's dropping your test grade work?
If you meet the attendance requirement, which is I gotta look it up because it changes from class to class, but usually it's 2
days absent.
Yeah. So 2 absences, two unexcused absences. As long as you don't go over that, then you can drop your lowest test grade.
Oh, thank you, Professor.
You're welcome, but take it easy. So you're in good shape. So, as long as you don't hit a stretch of absenteeism, you'll be fine. So then that test can go away. And then, the only thing is the trade-off is that you'd be on the hook for the final exam. But, like for a lot of folks, they hope to be able to take the 3 tests, have an average that they're happy with and not have to sit for the final. But, like having the bailout of not having, to have a bad grade count, that's the important thing too,
I want to know that to get the limit does not exist for this one. This one has to not equal these two.
Correct. Either of them. Once you get one different limit, then you've showed
just
that the limit
doesn't
doesn't exist.
exist. Oh,
Exactly.
Have a good day, Professor.
You too, but take care. All right, so then we're on page 56. All right, so then partial derivatives, second order partials, all that good stuff. We'll learn about tangent planes tonight. All right, so number 3 is a pretty funky looking one. 4 is even funkier because it's asking for all 4 second order partial derivatives. But here it's just saying the partial with respect to y. All right. I suppose it didn't need to be a separate question because we got to do that anyway in order to answer number 4. But just to have a standalone question where we're just focusing on y, I think it's a good idea because it's kind of hard if you're not accustomed to this to think of something like cosine of x as a constant. We're treating it as constant. All right. So partial with respect to y. So this is a constant multiple. We're treating it as a constant multiple. All right, and so that would be the same for the other x. All right, the one that's in the power of e. All right, so what I'm going to do is I'm going to differentiate around the sine of x. I'm sorry, the cosine of x. So I'm going to leave that as part of my solution and then take the derivative of the other part in terms of y. So the derivative of sine is cosine, so we're going to have cosine of y. All right, it's with respect to y, so it's not like implicit differentiation where I need to slap on a dy dx. It's just going to be times cosine of y. Then minus, when I take the derivative of exponential e, that's not a highlighter. The technique is to rewrite as is, so e to the xy, multiplied by the derivative of the exponent. All right, my derivative of the derivative of the exponent, and I'll just kind of make a little note here. It's really saying d dy of just xy. So x is the constant multiple. We're treating it as if it were like a 2. All right, so yeah, you're right. It is going to be x. So I'm just going to pop that in there. But basically what we're doing, just as a quick justification for it, let me just make this look a little nicer. We're applying the power rule. All right, I'll just pop a power of 1 here. We're doing power multiplied by coefficient, reduce the power by 1. All right, because that x is taking on the role of a coefficient. All right, it's just some constant value. Now, for exponentials, we always multiply by the natural log of the base, so times ln of e. It's just when the base is e, it goes to 1 anyway. The reason I'm bringing this up is because I have the utmost confidence that you can all find the derivative of exponential base e. But if I throw an exponential base 2 at you, I have the utmost confidence that most people are going to forget to multiply by ln2. All right, so that's why I'm bringing it up here. It's always been there. It's just we never write it because it cancels out immediately. All right, ln v is equal to 1. All right, but if this were 2 to the xy power, we would write 2 to the xy times x times the natural log of 2. All right. So just something, old Calc 1 stuff that you should always be mindful of. And actually, I don't even know. I mean, it used to not be in Calc 1. Originally, it was the first part of Calc 2 was when you got into exponentials and logs. Then they changed Calc 2 completely, Calc 2 and Calc 3. They moved sequences and series used to be in this course. They moved it to Calc 2. And in theory, exponentials and logs was supposed to be moved to Calc 1, but not everybody got that memo. So what happened was there was a whole cohort of students coming out of Calc 1, going through Calc 2, having never learned how to take the derivative of exponential or log functions. And then you get to me, and I'm like, well, of course, the derivative of natural log is 1 over x. And they're like, whoa, when were we supposed to know that? So if I'm slowing down and boring you with some of these rules, it's kind of for that reason, because I don't always have a whole heck of a lot of confidence. They're like, sorry, that's the faculty law. And I'm like, oh, sorry, I'm faculty. They're like, oh, really? I'm like, listen, I dress like a slob, I know, but I don't care. Yes, I am a teacher here. Well, how long have you been here? You must be new. I've been here for 20 years. And they're like, oh, you've been working here longer than I have. I'm like, yes, I have. Please leave me alone now. So, oh, I got stickers, I got everything. They just assumed that I was not doing the right thing. And the one thing I don't ever appreciate is when somebody is assuming that I'm not doing the right thing, but then they cop an attitude with me about it. Like, give me a chance to show that I'm doing the right thing first. And then if it turns out that I'm not, then it's like, sir, you can't park there. Like, first find out that I'm not supposed to be parking there before you give me that. That person blocked my car in. Like, I was walking out to my car. The security car blocked my car in because they thought that I wasn't supposed to be there. And I'm like, not only is there a sticker there, but I've been working here for 2 decades. Like,
Should have been like.
do you know who I am?
You should have been like, I go golfing with your supervisor. You know that?
Oh, that's a good one.
But they do that at night when you go home. They always stop people. They don't think they're students.
Yeah.
Even though I have a sticker now. They would just stop and, what are you guys, wacky or what?
Yeah, like, I understand that there's like there's bad eggs that cause problems for other people, but just don't assume that I'm causing trouble. When I'm causing trouble, you'll know. I'm not really in trouble, but I do sass people back when they give me a hard time. Yeah, second order partial. So we have a first order partial with respect to y. So I need a first order partial with respect to x, and then I need those 4 second order partials. So you can tell that I gave just the appropriate amount of space for you to do all this work. I gotta stop standing up, my knees are killing me. So I might as well start off with the y's, all right? So I'm just gonna clean up this one just a tiny smidge and write it as cosine x cosine y minus x e to the xy. Just a tiny little bit, just to make life a little bit easier. I'm also going to use the other notation, f sub y, because as fancy as the delta of f delta y is, and as cool as you feel writing it, it does get a little old having to write that over and over again, especially for the second order stuff. So f sub yy,
What happened to the natural log v?
ln of v is equal to 1. So that's going to cancel. All right, so when I'm taking my second order partial with respect to y, I'm basically doing the same thing that I did previously, just with my first derivative. So I'm going to hang on to the cosine of x. I'm going to take the derivative of cosine of y, which is negative sine of y. Now, for the second piece, it's actually not bad when we do it with respect to y. But if I had to do it with respect to x, it would be kind of problematic because one way that x is treated as a constant. The other way, it would be a variable, in which case you'd have to use product rule. Right? So in this case, it's not bad. So minus x as a constant multiple, rewrite e to the xy as is, multiplied by the derivative of the exponent, right? So derivative of the exponent, again, is just like we did before, is just going to be x. And then the natural log multiplied by the natural log of the base, ln of e, which immediately, again, cancels out. All right? So we clean it up a little bit. At this point, it's really not necessary to because we're not doing anything. We don't need third order partials, at least until I get to the next page and find out that I'm completely wrong. I honestly don't remember. So minus x squared e to the xy. All right. So not terrible, but now I need f sub yx. All right. So f sub yx, taking the derivative with respect to x now. All right, and that spices things up a little bit. So that's telling me that I'm hanging on to the cosine of x. I'm sorry, cosine of y, because that's the constant multiplier. Then I'm going to take the derivative of cosine of x, which becomes negative sine of x. That's not the part that makes it spicy. It's this part over here. I now have to take the derivative of that using the product rule. Because x is the variable of interest, and what I'm looking at is the product of two functions, x and e to the xy. In the other context, when I was differentiating with respect to y, that x was treated as a constant multiplier. So yeah, I could have used product rule, but when I went to take the derivative of the constant, it would have gone to 0 anyway, right? So minus the first function x times the derivative of the second with respect to x. So e to the xy. So I'm treating y as a constant multiplier. So the derivative of, really I can think of that as yx is going to be y times ln of e, which again immediately cancels, plus the second function, e to the xy, times the derivative of the first, which is just a 1 anyway, right? Because it's, again, with respect to x. So changing your perspective is very, very critical here. Now, we talked about this very briefly last class, but it is a critically important relationship, and that is the idea of mixed second order partials. So I can show you again, but I don't think I need to, / I don't think you want me to. Last class we went through all 4 of the second order partials, including the mixed ones, and we determined that f sub xy and f sub yx were the same exact thing. So if your function and their derivatives are continuous, then your mixed higher order partials will all be equivalent. All right, so function and its derivatives continuous mixed higher order partials are the same. All right, terrible penmanship, I know, but it's saying the function and its derivatives are continuous, then the mixed higher order partials will be equal to one another. All right, so that's telling me that even though I just did all that work to figure out what f sub yx is, that's also going to be the same as f sub xy, which is hugely important, right? Because in order to figure out that last second order partial, I need my first order partial with respect to x, and then I just need it again with respect to x. All right, so that's an easier pathway than having to do pretty much everything I just did in order to just come up with the same answer. All right, so very, very important. Now, how do you assess continuity? Well, we spent time talking about that, but basically in a nutshell, it's talking about the idea that it's not going to be undefined or imaginary for any x value, right? So, or y value. So if I had an ln in here, all bets are off, all right? Because ln is not continuous for all values of x. All right, now if I have a restriction on my natural log function, all right? So if I'm not saying natural log from negative infinity to infinity, then it's fine, because I could make the restriction that I'm only looking at values of x that are greater than 0, all right? But you can think of other situations. Throw in a radical, throw in a denominator with a variable in it. It tends to mess things up, all right? So for the other second order partial, what I want to do again is go right back to scratch, which kind of sucks. Oh, I did have extra partials there for the same thing. Okay, well, it is what it is. I think that might be overkill. So my first order partial with respect to x, I'm holding the sign of y as constant. taking the derivative of cosine of x, which becomes negative sine of x, minus e to the xy, yeah, that's the derivative, times the derivative of my exponent with respect to x, so that's just a y, times the natural log of e, which again cancels immediately. We still need to find the second order partial with respect to x, so it's still part of 4. I'm just writing it up there for space. All right, so you may have kind of thought about this and said, oh, do I have to keep writing that ln of e? You never had to write it. I'm just writing it every time because I figure if I do that, then when it is something like 2 to the xy, you'll be in the habit of writing the ln part, right? So it's something that I'm trying to do to kind of help you from making a careless error down the line. Bless you. All right, so now I need f sub xx. And that's the last thing I need. Because I don't need f sub xy because I already figured that out indirectly. So taking the derivative of this with respect to x, which means all my y's are constant multipliers. So sine y, hang on to that. Negative sine x has a derivative that's negative cosine of x. Now, that ye to the xy, when it was the mixed second order partial, then it was a product rule situation. But now it's not going to be like that because the y is treated as a constant multiple. So much simpler. So minus y, e to the xy, times x, times y because it's differentiated with respect to x, times the natural log of e. Again, kills the ln of e immediately. So negative sine y, cosine x, minus y squared e to the xy. Phew, Jackman, look at that. It's crazy. Look at all that work. And we still don't even know what this is used for. Right now it's just an exercise in just doing derivatives for the hell of it. We're going to see in a couple minutes what it's used for, though. And it's pure excitement.
So it's always good to do all 4 then, just to get used to it.
Yeah.
To do the f of x, do the f of y, do the f xy, and the fyx.
Right, for at least for practice, but then, you know, like once you get a feel for it, then you start saying, all right, if I need to get mixed second order partials, what's going to be my easier pathway? You know, that's the thing. So like, for example, in number 5, where I'm doing a third order partial, mixed partial, like I have to do f sub x, y, x. So I would look at everything that I did here for my my second order partials and decide, all right, well, which is going to be my easiest way, my easiest pathway to get where I need to go, all right? So, because like this kind of question, I mean, yeah, it's building off of work that we already did, but imagine it's a standalone question on a test, right? You don't want to have to do all of this work just to figure that out. So what you would do is you'd say, okay, if I know that all mixed third order partials are going to be the same, then what's going to be my easiest way to get there? So f sub x, y, x, we know that that's going to be the same.
Oh, sorry, I didn't follow that. I mean, I don't understand what that symbol stands for. Is it saying it's the second order of the first one?
The second
order is y of x after f of x?
For this one?
Yeah.
This is saying first order partial with respect to x, second order partial with respect to y, third order partial back to an x. But this is going to be the same as f sub x, x, y, f sub y, x, x, f sub, well, I got x, y, x. So what am I missing here?
Why?
Y, no, there should only be one y. Do I have it all? No, I think I have it all, yeah. Okay, that's why I can't figure out another one. All right, so all three of these things are gonna be the same, assuming, again, that your original function and its derivatives every step of the way. All right, so once if I'm looking for a third partial, my second order partial needs to also be continuous. All right, continuity is the key to everything. All right, so I have three possible pathways to get to the required value that I want. So I could even look at this and then say, well, f sub x, x, y, y. You know, just change up the ordering of it because the different permutations still lead to the same outcome. All right, so I look at all of this work and I say, well, it doesn't matter because I already did it. But if I'm starting from scratch, I'm liking this one. I'm liking this one more than I'm liking the others. All right, because starting from scratch, I can take the derivative with respect to x, then take the derivative again with respect to x, and then it's only at this step that I would take the derivative with respect to y, right? Which is going to be a lot easier. All right, so I'm going to pop a star on that because I got you going on it at least, and then let you play around with that. So we're looking at f sub x, y, x. So if we know what the derivative of f, second order partial with respect to x, y, if we know what that is, then all we have to do is find the derivative of that with respect to x, all right? And then once we have that, take that result and find the derivative with respect to y, all right? So we're looking at this guy right here, and we're going to find its derivative. So f, for quality f, obviously, f sub x, y, x all right, that's going to be equal to, so we're taking the derivative with respect to x, so we treat y as constant. So I'm going to hang on to my negative cosine y and then differentiate the x part, right, or the sine of x part. So sine of x has a derivative of cosine of x. Then the second piece, that's kind of a little bit on the aggravating side because we have two factors that make up a product. I have this guy here, and then I also have this guy over here. All right, so product rule is going to be in play. I'm going to incorporate the negative into the factor of negative xy. So it'll just kind of work its way out with the distributive property. So first, negative xy times the derivative of the second. All right, so e to the xy times the derivative of xy with respect to x, which would just be y. So times y, plus the second function, e to the xy, times the derivative of the first function with, again, respect to x, so times negative y. All right, and then the last piece is a standalone function. We take the derivative with respect to x again, so minus e to the xy times the derivative of the exponent with respect to x, which is going to be y. All right, so if the question were just find the derivative f sub x, y, x, I would leave it like that, but since I have to take the derivative of this also, I think it kind of serves a good purpose to simplify, just to make life a little easier for the next step. All right, so the first part's not going to really change very much. Not going to change at all, actually. Second part, I'm going to write it as negative x y squared e to the xy minus y e to the xy, and then minus another y e to the xy. So So those can be consolidated. So maybe you do that all in one step. Yep. Drop my pen. All right, so f sub xyx would be that lengthy expression.
I did fxxy and got something different. Shouldn't they be the same thing?
They should be the same
'Cause I
thing.
didn't get that last term you have.
Huh. So one of us screwed up. Because it's continuous, so the derivative should be exactly the same. So let me double check my work.
Oh wait, I see.
You see it?
Yeah,
Okay.
you're good.
All right, thanks. All right, so f sub xy xy. So now I'm differentiating this with respect to y. All right, so just more of the same. So my function of interest is y, or my variable of interest, I should say. So I'm going to hang on to the cosine of x, negative cosine of x. Differentiate just the y component. Derivative of cosine y is negative sine y. All right. The second piece and the third piece will involve products. So, and again, I'll extend my first factor to include the negative sign. So first times the derivative of the second with respect to y. So times e to the xy. Derivative of the exponent with respect to the y term would be x, plus the second function, e to the xy, times the derivative of the first with, again, respect to y, which means I'm applying the power rule here, treating the x as a coefficient. So negative 2xy. Then I'm going to do the same thing, or I'm going to apply the same concept, just with a negative 2y and an e to the xy. All right, so first, negative 2y, times the derivative of the second, so e to the xy times x, plus the second function, times the derivative of the first, which is just a negative 2. All right, so the last one, f sub xy(x) was pretty gnarly, and this one's even worse. But there's no need to simplify because this is all we have to do. If you do simplify, maybe some things will consolidate, maybe some things will even cancel out, but it's not worth the time it takes to do it. All right. So we're going to talk tangent planes. Tangent planes are cool. You know, when you're talking about two-dimensional functions, you know, like a parabola or something like that, when we're talking in terms of rates of change and things along those lines, tangent lines, instantaneous rates of change, that seem to make sense. Okay, so a two-dimensional figure to assess a rate of change for another two-dimensional figure. So it would make sense that if we span up to 3 dimensions, now what we would be doing is looking for a 3-dimensional way of representing that rate of change. Okay? Because, yeah, like you're walking up a hill, right? So it doesn't matter how steep it is. I mean, let me just put it to you this way. If you're going hiking, you could make it as steep as you want. Right, so Breakneck Mountain, I don't know if you're familiar with that. I don't go hiking a lot, but I like Breakneck because like they had the easy trail and then they have like the more challenging trail. and then you could just climb up the cliff face if you want, you know, like you could go nuts with it. But basically the path that you take dictates the rate of change that you're gonna experience along your route, right? So if I wanna go a zigzag approach, my slope, my gradient, if you will, we'll get there, is gonna be not as steep as the person's going up the cliff face, right? So it really does depend on the direction in which you're going up or approaching a particular point, right? So a tangent plane helps us do that because it's an omnidirectional way of representing a rate of change. Because if I have a plane that's gonna be tangent to a point, then I can move along that plane any way I want and still get a sense of the rate of change, all right? And we are gonna learn about gradients. Gradients, again, is just a three-dimensional way of representing slope. Actually, it's not just limited to 3 dimension, but that's what we're gonna focus on. The term slope is actually just the 2-dimensional way of thinking about gradient, right? Because really, if you're talking about, like I said, climbing up a hill, walking up a hill, the slope is just, you know, take a cross section, take a knife and just slice right down vertically down the hill, and then just map out that pathway that is the intersection of that cut and the hill, you know, that cross section, just the perimeter of it. That's your 2-dimensional rendering. The tangent line, instantaneous rates of change, the secant line, all that stuff, all that's doing is just focusing on just that one possible pathway. We want to be able to focus on any possible pathway. So what I used to do in this course was actually derive the tangent plane approach, and it in and of itself took up like a whole class session. So what I did was I along with, you know, learning and stuff, but one thing at a time. All right, so rules, we got rules, plenty of rules. Suppose that f(x, y) is continuous first order partial, so continuous continuity is hugely important. So why do we spend time on domain and continuity? Because of that. Normal vector to the tangent plane at z, at AB, is going to give us this relationship. And so you got to be really careful, and people easily lose sight of this. If I were you, I'd make a note. These are first order partials, right? Because people look at this, and no matter how many times they look at it, all they keep seeing is f of a comma b. All right, so what we're looking at here again is first order partials. That's the one drawback to this kind of notation. Because up until this moment, f of x, f of y, always just meant plug those values in and call it a day. This is the first order partial with respect to x, so I'm taking the derivative with respect to x and also with respect to y, and then putting in my AB value. All right, so that's a normal vector, those values, and then a -1, all right? Most people look at it as like, whoa, that -1, where is that coming from? It actually comes from the solution to a reduced row echelon technique, so row reduction, you know, RREF that we did in our calculators. So that part of the solution bears itself out, and there is a reason for it, but that's something that you would look at the activity for. Further, an equation of a tangent plane is given by this, all right? So you see here we have just that naked f, right? That's the original function with, evaluated for a and b, all right? So you have the recipe for the tangent plane, it's very easy. But again, if you want to know where all this stuff is coming from, then you go to the activity that I'm posting in a little bit. The equation of a normal line through the point is given by these functions, right? So, but that's really not what the first part of the question is asking, so we'll focus on tangent planes first, all right? So this looks like an overwhelmingly difficult question because I gave you 4 coordinates, which means we have to come up with 4 different tangent plane equations. This is gonna take us the rest of the night. Actually, it's super easy, barely an inconvenience. It's gonna take like 5 minutes maybe, because these points are hand-picked because they're actually very convenient. All right, so first what I need is my function. It says z equals. How about f of x comma y instead of the z? So then when I'm looking for my first order partial with respect to x, I'm treating y squared as constant multiple. So I'll just put that down first and then multiply by the derivative of the x component. So just a 2x. Clean that up ever so slightly and you get 2xy squared. All right. We'll worry about our partials first and then we'll tackle the coordinates. All right. The second partial that I need, first order partial with respect to y, I hold the x squared as constant and then take the derivative of the y squared term, which is going to give me a times 2y. And so what I'm looking at here is 2yx squared. All right, so, compare this to what we did with that sine cosine function with the e in it. Much easier, right? They're not always going to be crazy difficult. The one went away because it's constant. We didn't have to treat it as constant. It already was constant, right? So now I want to tackle my tangent planes. So at 1, 1, I'm going to find my different components. All right. So I need f of 1, 1. First order partial with respect to x at 1, 1. First order partial with respect to y at 1, 1. All right, so very easy calculations. Plugging in a 1 for x and a 1 for y. So 1 squared times 1 squared is 1, plus 1 is 2. So I got that bad boy. Two times 1 squared. 2. 2 times 1 squared, 2. So all these calculations were very easy. And so my tangent plane,
Isn't F 3?
is it 3?
Because it's 1 squared plus 1 times 1 squared.
The 1 squared.
Oh, wait, I'm an
Yeah. Oh, not, yeah, it's 2, not yeah that you're an idiot. So, be clear about that. So z equals f of a comma b, f of 1 comma 1, which is 2, plus first order partial with respect to x of 1, 1, which is 2, times x minus a, the a value is 1, plus my first order partial with respect to y, add 1, 1, which is 2, times x minus the b value, which is also 1. And that's the equation of the tangent plane. So what that means is that if I plot the point at 1, 1, now remember, this is a three-dimensional surface. All right, so 1 is the x, 1 is the y. The z value is 2. So the coordinates are 1, 1, 2. This is the equation of the plane that would just touch the surface at that point. All right. Now, it doesn't look like our plane equation, which is normally ax plus by plus cz equals d. But if you clean this up and simplify, that's what it would be. All right. So when we talk about that vector, that f of a comma b, first order partial with respect to x, first order partial with respect to y, both at a, b, and then -1, that's coming from the solution because if I brought the z over to the other side, it would become -1z. So the coefficient of x, of y, of z make up your normal vector. And so coefficient of x is equal to the first order partial with respect to x. Coefficient of y, oh, this is supposed to be a y, is equal to the coefficient of y is the first order partial with respect to y, and the coefficient of z is always going to be that -1 because it's always in the form of z equals. So if I were to move it over, it's always going to be a negative z. All right, but let me make this a y as it ought to be. And so you think to yourself, dang, I got to do that 3 more times? Well, yeah. So at 1, 0. So I need f of 1, 0. So I plug in a 1 for x, a 0 for y in my original function, and I'm going to get 1. Now, it seems harder than it is because anytime I incorporate a 0, it's going to streamline things. So f sub x and f sub y both involve a product of x and y in some capacity. If I know one of them is going to be 0, doesn't matter if it's the x or y, both of these partials are going to 0 out. Which means, just looking back at this, yeah, z equals 1.
Was 0, 1 the same thing?
0, 1 is going to be the same thing. Yeah, same thing. Because we know that the partials are going to 0 out. And if you plug in a 0 for x and a 1 for y, it still simplifies down to just give you a 1. All right? So that happened a lot quicker than you might have expected going in. At 0, 0, well, we know the first order partials are going to 0 out. It's just a matter of what the original function is going to be equal to when x and y are both equal to 0. Still 1. So really not difficult at all. Now, the second one, a little bit of a different story. Because we have a cosine function containing both the x and the y, so when I'm looking for my partials with respect to x, it is going to involve some chain rule. All right? The function itself, it's an interesting looking function. I mean, you look at the graph and you say, wow, that's pretty cool. That's like you drop a pebble in a pond. Calm water, you drop the pebble, and then it creates that rippling effect. Yeah, well, now you know what function would create that model, so that's kind of cool. All right, but, it's still the same structure. So I have my original function, f of x comma y, which is equal to the cosine of, I'm going to write it as x squared plus y squared to the 1/2 power. Not for evaluating that function, but just to make life a little bit easier when I find the derivative. So first order partial with respect to x, keep it at, the inner function as is. Derivative of cosine is negative sine of all that stuff on the inside. But then I need the derivative of all that stuff on the inside, which is going to be 1/2 x squared plus y squared to the negative 1/2 times the derivative of the innermost part of that function. All right, this is with respect to x, so the y squared is going to go away, so I'm just going to be left with a 2x. Now, worth it to clean it up? I don't know about that, not yet anyway. So let's just leave it as is until we have a reason to go further. All right, so f sub y, same Really, it's the same exact thing right up until the very last step. All right, because the only part where we're actually actively taking the derivative of something involving either an x or a y was the part where we were taking the derivative of the x squared plus y squared. Right? Everything else would pan out the same way. So I need the equation of tangent plane and tangent line to the surface at these points. All right. So, oh, that reminds me, I forgot the normal line in the last one. Honestly, it doesn't really bring anything to the party. I'll take it as a typo. Because really it's the tangent plane stuff that I care about for now. So at pi 0 is my first point of interest. So f of pi comma 0 so I'm plugging in a pi for x and a 0 for y. So I just play this out logically. If I take the pi and square it, and then raise that pi squared to the 1/2 power, the 1/2 is going to cancel the power of 2. So it's really just asking for the cosine of pi, which is -1. All right. You know, you could pop it in your calculator, but I feel like, you know, just taking a second to logically reason it out, I think that pays off a little bit quicker for you. All right. So for f of f sub x, now here's where the payoff really happens. Because if you're always defaulting to going to the calculator, and you know me, I'm calculator all day, every day. But if you're defaulting to that, then you're missing out on an opportunity to find some shortcuts, right? Because we know that the inner function here for pi 0 is going to go to pi. What is the sign of pi? 0, which means all of this is zeroing out. All right. So much easier to do it that way than even typing it into the calculator. All right. First order partial with respect to y is the same ingredients. So if it's zeroed out for a first order partial with respect to x, then why wouldn't it do the same thing for y? So that's going to zero out also. And after all of that, we get the tangent plane at z equals -1. All right.
Sweet.
Now we do the same thing at 0, 0, but there's no reason to think it's gonna play out any differently, because whether it's the sine of 0 or the sine of pi, you're still on the x-axis, unit circle. On the x-axis, the sine function is always equal to 0. All right, so f sub 0, 0. All right, so plug in a 0 here, you're looking for the cosine of 0,
1.
which is a 1. And my first order partials with respect to x and y are both going to be equal to 0, because in either case, I'm taking 0, squaring it, square rooting it, whatever, but the sine of 0 is equal to 0. And so we're going to get the tangent plane being equal, or giving us a tangent plane where z is equal to just a +1. All right. So we got a lot of -1s, +1s. There's only the one instance where we got something other than that. All right. So these tangent planes are of the horizontal variety. All right. So parallel to the xy plane. All right. So if the plane is in the form of z equals some constant value that we can call a, then plane is parallel to xy. All right. Most importantly, what that means is that you're looking at an extreme value. All right. So it's giving us extrema. Relative max, relative min. You know, you might have learned them as local max, local min, but it's the same thing. Just because if you had turning points in 2 dimensions, there had to be something that is consistent with turning points in 3-dimensional system. You can see the little hump there. There is a little peak to that mountain. What we just discovered is that that peak is happening on the plane z equals 1. All right? At pi, comma 0, which is one of these points along this ring here, it's kind of hard to see, but if I bring it in a little bit, this ring here would be the fold that represents the lowest points along that graph. All right? So you have a peak and then it's bowing outward. Right? So so you have like the hill and then you have the valley. But it's happening in every direction, so it's not as obvious. So, you look at something like this, but it's also happening like this, in every possible direction, right? But every one of those valleys is corresponding to a local minimum.
So it's
And
negative 1.
and that's
Yeah.
happening at the plane z equals -1.
Is it negative or 1 because those are the extremes of cosine function?
Yeah, it's actually, as it turns out, yeah. And specifically because the amplitude of that cosine function is equal to 1. So if we had z equals 2 times the cosine of all of this, then our planes would have been z equals -2 and +2 for the extremes, right? But basically what we are looking at here is a cosine function in 3 dimensions, right? Because if you take that cosine wave and propagate it outward, but going in every direction, and then connect all of the peaks and all of the valleys, you'd end up with this surface. Right? Which is why we don't spend a whole heck of a lot of time trying to draw these things, because it's a nightmare. But we can still evaluate them. Now, a little notice here, what is the equation of a tangent plane at extrema? I just kind of gave it to you. It's z equals some constant value a, right? But as it's been turning out, if you know that the extreme value is occurring at AB, then it would be z equals f of AB. All right? But again, that's assuming that the extrema occurs at AB. So the next logical progression in all of this is making a determination of the A and B values that correspond to extrema, right? Because in these cases, we were given the extreme values. We were told 0, 0, and pi 0. But what if we're given a function and they don't tell us anything? They say there are some extreme values, find them. That's a different story altogether. In order to be able to handle that different story, we need to learn about the chain rule for functions of several variables. Okay, because what we could be dealing with are nested functions where you have a function inside of a function inside of another function. Right? I find that tree diagrams, and this is kind of the standard approach, but tree diagrams end up being the most useful way to keep your thoughts organized when it comes to stuff like this. I didn't really buy that the first time I saw this concept. I kind of try to just Ted Can my way through it, which is basically my way of saying, I got it, I'll just do it my own way. And then it actually turned out that this is one of those situations where the prescribed way of doing it is actually, I think, the best way of doing it. Right? So we have a function z equals x squared e to the y, where x is equal to t squared minus 1, and y is equal to the sine of t. It's asking us for a derivative of z with respect to t. All right, so the rate of change in z corresponding to rates of change in t. All right, so we got to think about what that means because there's multiple layers here. Because if I'm taking a derivative of this function, there's two ways to handle it. I could find the first order partial with respect to x, or I could find the first order partial with respect to y. I think group texts are like the bane of my existence now. Because it's like whatever is being communicated generally never applies to me, but that doesn't mean that I'm not going to get like 40 messages.
And it's like the same two people texting back and forth.
Generally. But now I know that one of my relatives is out front of another relative's house in Virginia. Cool. Got it. Yeah. So once I take the derivative, the first order partial with respect to x, I can then, well, I can go a couple of ways. Well, in this case, well, it's only in terms of t, so actually there's only one way I could go. I could take the first order, or the second order partial with respect to t. So that would be, now it's a function of one variable at this point, so I would say, but you can still use the partial derivative notation, but I would be looking at the derivative of x with respect to t. All right. Now, if I take the first order partial with respect to y, the next part of the process would be to take the partial derivative of y with respect to t. All right, all of that is going to amount, those two pathways are going to amount to the derivative of z, which again is just another way, z and f are interchangeable with respect to t. All right, now we are going to tackle some cases where, you know, the second, the embedded equation could be a function of two variables itself, right? But these are the two different pathways that we could go in order to get to our result. All right. So what that gives me is a recipe, and really that's what's detailed here. The derivative of z with respect to t is the product of each element of the pathway. So partial with respect to x, partial of x with respect to t, and then the other pathway, so this is an OR situation, that's why a tree diagram is a reasonable way to go, because each pathway is a different possibility, right? So in probability, now I don't know how much experience anybody has with that, but probability in statistics, and means multiply, generally I'm oversimplifying, but OR means add. Right, so it's either this and this multiplied, or this and that. So this times this plus that times that. So from my vantage point, rules are rules. I mean, there's a time and place for them, but I don't find value in those rules because I could just kind of invent them on the fly. All right, so what I would do at this point is take a look at my ingredients and say, okay, well, these are the things I need. So my first order partial with respect to x is going to be 2x times e to the y, because e to the y we're treating as constant. All right, there's no x in the e to the y, so e itself is a number. So that's like saying 2 to the third. You know, well, what would that be? It's just a constant multiple. All right, so then the derivative of x with respect to t is going to be 2t. So I'm going to multiply these two together, and that's going to give me 4xt e to the y. The other pathway was partial with respect to y which I'm gonna hang on to the x squared, and then take the derivative of e to the y, which would be e to the y times the natural log of e, which goes away immediately. And then the partial of y with respect to t, which is going to be cosine of t. Multiply those two things together. And, you know, it's going to look ugly, but we'll take it. We're going to have x squared, e to the y, cosine of t. Add those two together, and that's your derivative. That's your derivative of z with respect to t. Oh. Poor people get too confused. That is a typo. Those should be partials. All right, so this is my blueprint for helping me find my derivative, but this is me actually carrying it out. So you see I found each piece, multiplied them together, and then took the two scenarios and their results and added them together. All right. The next example is a little bit more elaborate because you could see x and y are both functions of s and t separately. All right, so here the tree diagram is going to be even more important. And there it is. So partial z with respect to s is really what I'm looking for first. All right, that's my first job. But really what I'm going to do is I'm just going to use my notation and detail out every possible thing I could take a derivative of. And then in order to find the partial with respect to s, I'm just going to take the relevant pieces from the pathways that emerge. All right, so I'm starting off with my original function f. I could take the partial of f with respect to x, or I could take the partial of f with respect to y. But then when I take the partials with respect to x, the partial of x, I could do that with respect to s or t. I do the same thing for the y's, again with the idea that I could take the partials with respect to both s and t. So partial y with respect to s, partial y with respect to t. I apologize, sometimes my deltas somehow magically start turning into 2's. They should really start, I mean, they should, if anything, look like backwards 6's. Some kind of bug there. Right, so this is what I'm looking for, ultimately. And these are all the different ways I could take a derivative from the information that was given. So what I want to do is I just want to go through this and identify any pathway that's going to get me to a partial s as a result. So starting with my original function, I could take the partial with respect to x and then multiply that by the partial with respect to s, partial of x with respect to s. Or I could follow this other pathway and ultimately end up with an s. So these are the relevant pathways. So starting with this guy, following this branch, or I can go with this guy and follow this branch. But ultimately, it's telling me the things that I need in order to find partial z with respect to s. All right. Now, ultimately, I also have to find the partial with respect to t, so I'm going to have to find all this stuff anyway in order to answer this question. But if I just needed that one thing, that's all the information I would need. Now, sometimes easier said than done because my f function looks a little on the funky side. Oh, okay. No, I thought it was a hand. So, looking at my original function, I could work with it as is, or I could clean it up a little bit. Cleaning it up would be like finding a common denominator and simplifying. You could do that, but you're still gonna have a radical in there. So, like, why kill yourself trying to do something like that? I mean, if it ended up being something that you knew was going to clean up just with a little bit of perseverance, then that would be a different story. But that's really not how it's going to play out, right?
Sorry, just to answer the first question, yes, you could either go to the left leaf or to the right side.
Right.
Either or.
But or means add the two. So it's like the mathematical or, which means you got to do both and add the results together. So it's unfortunate, but or makes it seem like you have a choice.
Yeah, I thought that's what it.
Yeah, probability, math, or means that you have to account for basically anything that satisfies the rule. So my original f, I could write it as, I'm going to make a slight adjustment to it, 1/4 x squared plus y squared to the 1/2 power. Nothing too crazy, just making it a little bit more power rule friendly. So that when I find my first order partial with respect to x, I'm looking at 1/2, 1/4 x squared plus y squared to the negative 1/2 times the derivative on the inside, which is just going to be 2/4 x to the first, so just 1/2 x. The y squared goes away because it's irrelevant. It's a constant, so constants go to 0. All right, and so we could clean that up a little bit, but we'll take the wait and see approach because I also have to find partial x with respect to s. All right, so 2t acts as a constant multiple, so I'm going to leave that in there, 2t. Then I just have to find the derivative with respect to s of cosine s, which is negative sine of s. All right. Then on top of all that, I have to find partial f with respect to y. Now that's going to have the same ingredients, except it's going to have a 2y at the end. So that's kind of nice. You can just kind of go into autopilot a little bit. Partial y with respect to s, taking my y function, t is a constant multiplier, sine of s has the derivative of cosine of s, so t times cosine of s. So what I need to do now is really what I did before, it's a little beefier. I got to multiply together and then add the results. All right, and you kind of pick and choose, you know, like, do I need to simplify, do I need to cancel, or there's some things I can combine a little easier, you know. Like, for example, I know that I have to multiply all of this by all of this, so why not get rid of the 2 with a 1/2, all right? I know that this is a negative exponent, so why not make it the bottom of a fraction and put it back in radical form? You know, a little simplifying on the fly kind of makes this less of a painful experience. Less of a painful experience. It's still going to be painful. There's no way around it. But like anything you could do to kind of streamline it is going to make your life a little bit more manageable. So I have a negative, I have a t, an x, and a sine of x. Sine of s, I mean. So negative x, t, sine of s, and I'll just chuck that 2 in the bottom of the fraction. And honestly, I do that just so I don't have to rewrite all of this stuff again with just like a multiplication symbol in between. All right, it's a little bit more fulfilling. The other one, same deal. The 2 and the 1/2 can go away. We're going to have a denominator of 1/4 x squared plus y squared under a radical. And then everything else is going on the top. So y t cosine of s. And I'll just kind of move that plus sign into a place that's a little bit more visually appealing. So those two together give you the derivative of z with respect to s.
What information does this give you?
What's that?
Like, what would this tell you?
Oh, it's the rate of change of your z function per unit of change in s, but without knowing what x, y's, s, and t's represent, contextually it's not really telling much of anything just yet. But we're going to learn about the extensions of all this stuff. All right, so I put a little star on partial z with respect to t, because really it's just following the other branches. So I have to find, we did this part already, but I need partial x with respect to t, partial y with respect to t, and then those products put all together. All right, so put a star on that one so you can talk from that on here. All right, so with the last couple of minutes, I just wanted to talk to you a little bit about directional derivative. It's pretty painless. So, I mean, there's objectives and all that stuff there, but you have like a little bit of a contextual component here. And so this is kind of what we're leading towards. So being able to find derivatives allows us to be able to combine the concepts that we learned with vectors and also this multivariable stuff. All right, so function f of x comma y is the height of a mountain range at each point where x is equal to x comma y. If you stand at some point x equals a, the slope of the ground in front of you will depend on the direction in which you're facing. That's what I was talking about before. All right, so you're walking up Breakneck Mountain, you're taking the easy path or you're going up the cliff. You know, so the path that you're taking will impact the gradient. All right, it might slope steeply up in one direction, be relatively flat in another, and slope steeply down in yet another direction. The partial derivatives of f will give a slope, partial f with respect to x in the positive x direction. All right, we could also do the same thing in the positive y direction. But we could generalize this to give us a slope in any direction. That's what the directional derivative tells us. This is the limit definition of that, and I promised you that I wouldn't bore you with that. But this is really what we're after here. So this is going to start the process of contextualizing this stuff so that we could actually make some good use of it. Now, you can see that the key components here are just simply finding partials with respect to x and y. All right, but it's also incorporating a unit vector, so that's coming into play also. All right, so I'll just do the first example and then I'll let you go, but it's easy enough so that you can start to get a handle on it. So partial with respect to x is just going to be 2x. Partial with respect to y is just going to be 2y. If I want the partial with respect to x at 2, 1, the relevant value to plug in would be the 2. I'm going to get a result of 4. Partial with respect to y at 2, 1. The relevant value to plug in is the 1, giving me a result of 2. All right. So what I need now is my unit vector. All right. So my unit vector comes from the given angle. All right. All related to the unit circle again. So the unit vector going to be cosine theta, comma sine theta. In this case, we're talking about pi over 4. So in this case, we're looking at cosine of pi over 4, which is rad 2 over 2. Sine pi over 4, also rad 2 over 2. And so my directional derivative, d sub u, at 2, 1, is going to be the dot product between those partials and my unit vector, right? So if we're looking at f sub x, comma, f sub y, and my unit vector u sub 1 and u sub 2, the directional derivative is the dot product between those two quantities, all right? So really all that means is just you're going to multiply your x components together. So 4 times rad 2 over 2 plus 2 times rad 2 over 2, which simplifies 2 rad 2 plus rad 2 to give you 3 rad 2. All right, so that's going to give us, based on this angle, the rate of change in our two variables. All right, so we'll talk about this a little bit more next class, but we restricted it down based off of the angle. But if I wanted to not make that restriction, if I want to have a function that would tell me what my rate of change or my steepness is for any value of theta, then we could leave it in general terms and work off of there. So we can create functions out of this, and that function would be known as the gradient. All right, so there's more to it, but that's enough to kind of whet your appetite, I think, a little bit. All right, so I'm going to put a star on number 2 so you can at least practice with that skill, and then we'll pick up with this next class. In most cases, there's always one direction where, or direction u, where the directional derivative is the largest. This is the uphill direction. In some cases, such as when you're at the top of a mountain peak or the lowest point in a valley, this might not be true. Let's call this direction of, call this direction of maximal slope m. Call this the direction of maximal slope. It's a typo for somebody. Both the direction m and the maximal direction derivative, d sub m of f of a, are captured by something called the gradient. All right, the gradient of f, and it's denoted by an upside down delta. All right, the gradient is a vector that points in the direction of m and whose magnitude is the direction derivative of the maximal directional derivative. Yeah, so that symbol, that upside down delta, if I'm not mistaken, I'll look it up, but I'm pretty sure it's NAMBLA, which is horrible. If you've ever watched a South Park episode, so I won't be using that term.
You like South Park?
I used to. I haven't watched it very much recently, but
Morty.
oh, it's NABLA. But it's so hard to not put the M in there, and it means something else, and so that I just don't say it.
With the no, explain.
Oh, I can't say it. There's absolutely no way I could say it. Okay? So I mean, you could Google it, but there's no way, absolutely no way. They also call it DEL for some reason. It's another way of saying it for the people who don't want to say NABLA, and for fear that it sounds too much like NABLA. Right? So they call it DEL, but it's not a delta, right? Because it's upside down, capital Greek letter delta. So yeah, I just call it the gradient, because that's what it is. You know, it's just not a symbol. Unfortunately, it's one of those symbols that doesn't really tell you I'd say anything about what it is, like dy dx. Like once you know that the d is derived from lowercase delta, and delta means change, then it kind of all fits together. But here, not so much, right? The gradient is going to be a vector value function that's related to the partials, all right? So you're finding the partial with respect to x, partial with respect to y, and then dotting that with the unit vector, all right? So basically it's what we did on the previous page, except you're not substituting in a number, all right? That's your gradient vector, all right? So that's really all there is to it, but there's properties of the gradient, specifically the magnitude of the gradient, that make things related to the gradient pretty worthwhile, right? The directional derivative in terms of the gradient, this is something that we've talked about, but I didn't use the term gradient. It's basically saying that if I were to find the dot product between the unit vector and the vector value function, that is the gradient, before substituting it in, that would be my directional derivative in general terms, right? Also, since we have another definition of dot product is uv multiplied by the cosine of the angle in between them. You could do the same thing here, and so find the magnitudes and then multiply them by the cosine of the angle in between them. Right, so it's just another relationship, but it's a pretty important one because this rule defines this relationship, right? Because we're talking about maximum change. If cosine is equal to 0, I'm sorry, cosine, the angle is equal to 0, then cosine is equal to 1. All right? So that would make your directional derivative in terms of the gradient equal to the magnitude of the gradient itself. All right? If your angle is 180, then cosine would be -1, so that would give us the magnitude, the rate of change in the opposite direction of the gradient. All right, so that's where all these properties are coming from, and it's pretty useful to know that piece of information. All right, but the examples they're not terrible because it's just saying find the gradient and then the magnitude. All right, so we've already done this work. Partial with respect to x was 2x. Partial with respect to y is 2y. So the gradient with respect to xy would be 2x I plus 2y j. All right, just multiplying it by the standard unit vectors. All right, no angle was given, so it's just I and j. All right, and so the magnitude of these would be the sum of the squared values rooted. So we'd be looking at the square root of 4x squared plus 4y squared. You pull out a 4 and root it, so you get 2 times the square root of x squared plus y squared. All right, so the same idea comes into play for the second one, so we might as well just bang it out. All right, I mean, you could just flip to the previous page and write down what we had for partial x and partial y, but I mean, it's easy enough to do, so we might as well. So 2x y cubed, 3x squared y squared minus 4y cubed. All right, so the dot product between that and the standard unit vector would give the gradient, so 2xy cubed I plus 3x squared y squared minus 4y cubed j, and the magnitude both of those values, those quantities squared, thrown under a radical. All right, so I'll just do that on the fly. 4x squared y to the 6th plus, I'm just going to write that binomial again just with a power of 2. Because really, I mean, just like that partial, the fourth order partial we did before, you would ask, okay, why would I distribute that out? And I mean, if there's a purpose behind it, sure, then go ahead, but it doesn't seem like there is, so we're just gonna leave it at that. And besides, the best I could come up with when distributing this out would be that somewhere along the lines I would have an x squared y to the 5th and a y to the 6th. They're not combining with the other terms anyway, so just leave it. Go back to this one real quick, because this is going to actually be a little bit more important now, right? So we're going to use this relationship here because this allows us to define it in terms of an angle. The reason why I was saying it was cheating is because I already know that -3 is actually going to be one of the special angles, 0 or 180, just because I created the problem. So you got to kind of look at it like, well, we don't want to use trial and error. We want to use a process that will allow you to solve for it. So something that will work in every case. So this is what I'm looking for. I need to use this relationship in order to get where I need to go, right? So the magnitude of the gradient vector multiplied by cosine of theta, all right? So is there a direction u in which the rate of change of the temperature function, units given, at these coordinates is -3 Celsius per meter? So, you know, like, again, it's not maybe something that you would necessarily consider, but I would think of it as, you know, any environmental situation where you're just looking for the path of least resistance. That actually, it doesn't even have to be environmental. It could be any situation. But environmental kind of, it's something that, you know, just pops into my mind. Like a fire, a high pressure situation, like you're in an area where there's high pressure and you need to navigate through that high pressure zone, right? Same thing with a fire. You get a blazing fire, you want to navigate your way through that blazing fire in the quickest way possible. This information, you know, would map that out for you. All right, so now in the middle of a fire, are you going to be doing those calculations? Of course not. The idea is to learn from the calculus so that you can apply the ideas in real life, not necessarily the actual calculations. All right, and so a direction where the rate of change is -3 degrees Celsius per meter. All right, so it's basically asking us for the gradient and then to figure out what angle would give us that particular measure. All right, so undo. Now this is in 3 variables. And you can see below, I mean, this is more of a discovery thing, but you could see below that that it's really just the same thing as a function of 2 variables. Right? But we will have to start thinking about what a 4th dimensional situation is going to look like, and I have an activity for us, or you know, I loosely use the word activity for sometime next week. So more on that later. So anyway, I'm gonna hit undo again because that seems to be the thing I have to do most frequently. T sub x, t sub y, t sub z. So with respect to x, I just get a nice 2x. With respect to y, I'm sorry, I get a 2y. That was weird. With respect to y, I get the 2x minus z. And then with respect to z, I just get negative y. Now they give us a coordinate, and that's all well and good, but let me start the process of defining my vector value function. All right, so t prime, my derivative, is the vector valued function 2y, 2x minus z, negative y. All right, worry about the coordinates in a sec. My neck is killing me. All right, so I want to dot that against u. All right, so it's the directional derivative, you know, it's a function. This is my derivative, but it's a function in terms of x, y, and z. I want to dot it against cosine, ijk. Well, that's cheating. I'll explain why in a sec. And magnitude of the gradient vector multiplied by cosine theta. So oh boy. All right, so that derivative and the gradient vector are going to be the same thing. And so what I'm going to do is find the magnitude of that and multiply it by the cosine of theta. And in theory, that result should be equal to negative 3. All right, so the square root of each component squared. And again, we're given a coordinate, so we could plug that in at any time. But like I said a few moments ago, I want you to have a technique that you know is going to work regardless of the situation. All right, so this is our setup. You have the rate of change as negative 3. So we know what this whole thing is supposed to be equal to. We just have to figure out what theta is. Now, what we have is an equation that will allow us to figure out any situation in which the rate of change is negative 3. All right? So we leave it like this in some cases because we want to have, you know, completely variable situation allowing for multiple possibilities to give you a result of negative 3. Or, you know, sometimes not even negative 3. You just define it as equal to a, where you could say, here is the function that you would use anytime you need to solve for a particular rate of change. All right, but now I can plug the stuff in. And it should be a fairly easy calculation because the numbers are quite neighborly. So if I plug in a negative 1 for y, I'm going to get a 4 here and a 1 here. If I plug in 1s for x and z, I'm going to get 2 minus 1, which is 1, so plus 1. Barring anything catastrophic. I don't understand. It's such a distraction. I gotta, well, I'm gonna close the door, but between her and the guy across the way trying to teach stats, it's an assault on the senses. So actually, I might even be misremembering which question this is because it's not gonna have that clean answer that I thought, but whatever, it's cool. I mean, there's also a possibility that I made a mistake, but we're looking at rad 6, cosine theta is equal to -3. All right, so cosine theta would be equal to -3 over rad 6. All right, so theta would be equal to the inverse cosine of that. And sometimes that's good enough, because if you want to have a clean-ish answer, then to represent it in the decimal form that we're about to get, maybe not the best way to go. But the inverse cosine approach isn't bad. Let me just get my calculator going here. Split screen action. Error domain. Okay, so I definitely flubbed something up, because I honestly remember this having a final answer of 180 degrees. And not only am I not getting that, I'm getting a domain error, which now that I think about it makes perfect sense, because the square root of 6 is less than 3, so that ratio is going to be smaller than -1, which doesn't work for cosine. So let's see where I flubbed this up. So 2y is good. 2x minus z is good. -y is good. I believe I produced the radical correctly when I plugged in the y value of -1. That became -2 squared is 4. 2 times 1 minus 1 is 1. -1 squared is 1. Schnitzel. Okay, so instead of staring at this for, well, I've already stared at it long enough, so we'd say not possible. I'm just going to say that for now. And then I know that the minute everybody leaves, I'm going to figure out what I did wrong, and I'll have to face the music next class. Be like, well, I screwed this up. That's why I got the wrong answer. Or maybe, I don't remember the moment, but it is possible that at some point I was like, you know what, 180, too easy. Let me just change it up a little bit. And in doing so, I changed it to something that doesn't work. It's possible, I guess. What can you do? X, Y, Z, yeah. Yeah, I'm not seeing it. I'm not seeing it. All right, well, I'm going to put a star on number 4, because that one definitely works. And we'll figure out next class what happened with number 3, and we'll also go over number 4 together. This we'll do later. There's no level curves, it's basically a visual representation of slope fields. Gradient slope fields. We don't need that. We have to do vector fields later in the course, and that's slope fields, but in a different sense. This gives you a sense of the slope by basically just kind of smushing a 3-dimensional figure down onto a 2-dimensional axis. Right? So what's happening is cross sections are created, and whatever the graph, the trace graph of that cross section is is plotted on the XY plane, right? But the issue with this is,
Isn't that just a topographic map?
yeah, that's exactly what it is. And so if you go through like the OpenStax textbook, what happens is you'll see an example or two like this, and then you'll see a topographical map, and then that's about it. Right? So there's more that I can do with this, but we have to learn some more content first. Right? So more on that. It really kind of doesn't fit at the moment.
What was that, tree root?
What's that?
What was that, tree root?
Later, but we'll come back to it definitely, just not yet. All right, because even that example there is too simplistic, and it doesn't really get the job done. Right. I just had an idea for a tech assignment, because I'm creating a bonus tech assignment for my linear algebra class, and I figured maybe I would do one for this class too. So every now and then I have these moments where I'm like, oh, that could be the bonus assignment. So maybe that's what I'll do. We'll see. Extrema and saddle points. So in Calc 1, you had local max, local mins, and points of inflection. Right. It's the same idea here, except we're calling them local max, local mins, and saddle points. Right? So a saddle point is a point on a graph that's neither a maximum nor a minimum. Right? But it does come through the analytic approach. So if you remember from Calc 1, in the process of solving for maximum and minimum values, you came up with a variety of x values. Like maybe you came up with 5 x values. And 2 of them were the extrema. One was a max, one was a min. The others were just there. You know, and you're like, well, what are the other ones? Turned out that they were points of inflection. Here it'll turn out that they're saddle points. All right, so points that are neither max or min values. All right, so what we use is what's known as the second derivative test, and another technique is called Lagrange multipliers. All right, the technique of Lagrange multipliers. So those are the two that we focus on because, again, a calculator approach doesn't really apply for stuff like this because how would you do it, right? Unless you have a 3D graphing calculator, and even still, it's not the easiest thing in the world to come up with. Now, generally, what I do, I mentioned this before, is I give you the graph on a test. So I'll give you a GeoGebra graph, and this one's beautiful. So it says find/investigate the critical points of the function, meh. And so you look at the picture and you're like, wow, there's clearly a maximum point right there. All right, so that's what I do for you because you don't have the ability to come up with a graph. But the thing is, some of the displays are so convoluted that it's kind of hard to see what's going on. Right, so something that looks like it might be a maximum value might actually be a point that doesn't exist on the function. Right, so it might be a point of discontinuity. Right, so these are things that you have to be careful about, but at least it'll get you in the game, and that's what we're looking for. Right, so this technique, and we'll talk about where especially this part of it comes from, probably next class. Because when we get into Lagrange, because we're going to do that in a little bit, that takes a lot of processing power. So I don't want to go too crazy tonight. And also we want to leave some time at the end for the quiz. So suppose that the function has continuous second order partial derivatives in some open disk containing the point a, b, and that my first order partials are equal to 0. All right, that part should make sense. The first order partials being equal to 0, that's saying that the rate of change is equal to 0, which really is just talking about a horizontal, all right? But it's a horizontal vector, all right? Because this is the horizontal vector of a vector value function, and this is the component of a vector value function, and this is the vertical one. So this is telling me that I'm looking at a horizontal vector. This is saying that I'm looking at a vertical vector. All right. Now, if you translate that to our understanding of three-dimensional graphs, horizontal and vertical really define the XY plane. All right. So what we're saying here is that we're going to get vectors that are gonna live in just the XY plane or planes that are parallel to that. All right, so if it's on the XY plane or a plane that's parallel to the XY plane, then it's gotta be a horizontal plane. All right, because if the Z axis is going straight up and down, then a horizontal plane is what we'd be looking for in order to identify extreme values. All right, so that's what this is really telling us. The discriminant is the thing that seems to come out of nowhere, all right? But it does have kind of a Pythagorean look to it, all right? And so we'll investigate where this comes from, but it talks about the second order partials, all right? Yeah, and so there's properties related to it. It actually might remind you, and this is a good thing, it might remind you of the discriminant from quadratics, b squared minus 4ac. It actually is very closely related to that concept, just in a different sort of way. Right? So we'll talk about where that comes from. It's a pretty cool origin story, and so I'm excited to share it with you. It's just, again, not tonight. So if my discriminant is positive, and my second order partial with respect to x is also positive, then there's a local min. If discriminant is positive and second order partial is negative, then there's a local mass. If the discriminant is negative, then it's neither a max nor a min, it's a saddle point. If it's equal to 0, this is the one that you don't want, because it means that this technique does not apply. It means you got to do something else. And that something else is the technique of Lagrange multipliers, which, in and of itself is not a bad technique. It's algebra intensive, but so is this. And so what ends up happening is you end up doing double the work, right? Because you did all the work to figure out what the discriminant was here, which is based off of second order partial. So you did all that work to find out that all of that work was unnecessary, and you have to use a completely different technique. All right, so you got to be careful. And I'll show you what that means in a minute, and how you can kind of avoid some of these things. First thing, this bad boy. First order partial with respect to x, first order partial with respect to y. So 2x plus 2, negative 2y minus, plus 6. They have to be equal to each other and also equal to 0. All right. So a lot of weirdness related to this. All right. So now, since very important, you might think, how can they be equal to each other if one's in terms of x and the other's in terms of y? There are situations where they'll both be in terms of x and y, and so that's the case where you have to be very careful. But in this case, all we're doing is taking the 2x plus 2 and setting it equal to 0, and we're taking the negative 2y plus 6 and setting that equal to 0. And so we get x equals negative 1 and y equals 3. All right, so these are my a and b values. All right, so if x is equal to negative 1 and y is equal to 3, then our two partials will be equal to each other and equal to 0.
Shouldn't it be negative 2x plus 2?
Yeah, because in my world, for some reason, that negative didn't exist. So then positive 1. Okay, so first condition is fine. Now I need my second order partials. All right, so f sub xx, f sub xy, f sub xy, or yx, depending on which one is more convenient. All right, in this case, they're both fine. We're looking at 0, 0. All right, because if
You just write the same thing twice.
It's y of x, right? The last one? f of y of x.
You wrote f x,
But
that's
they both-
f That's why.
Oh, thank you.
Why?
I was walking and chewing gum at the same time, you know, speaking and trying to write, and I didn't do either of them correctly. Because actually I put the zeros down and that wasn't even right. So -2, -2, and then 0. Right. There was a 0 there, but not where I put it initially. All right, so this part is really a good indicator for us, right? Doing this work, because we just don't want that discriminant to be equal to 0. As long as, really, if you think about it, if either of these two parts are 0 and this one is 0, then it's gonna 0 out. If that's the case, then stop doing what you're doing, all right? So you get to this part in the process, before you even write the formula out, you would say, okay, non-zero values for f sub x, x, y, y, good, all right, then this technique is gonna be fine, all right? If either of these two are equal to 0, then this product becomes 0, and then that ends up, if this second order of mixed partial ends up being equal to 0, then the whole thing zeroes out, all right? So analyze what you have here before you pop it in there, just making sure that you don't have too many zeros, all right? 1 0 is fine. If you have exactly 1 0, you're gonna be okay. If you have more than 1 0, it depends on where those zeros are, right? Because if they're both for the first two partials, then it's okay, because the last one would be whatever the discriminant is, right? But that's the only time you have to care. So just basically 1 0 or less, you're good to go, all right? So I could pop it in. Now, it's the discriminant at 1 3, but there's no variables anymore, so I don't really need that piece of information. So we get a result of 4, all right? We also need our second order partial, f sub xx. We need to know what kind of sign that has, all right, if it's positive or negative. In this case, it's negative, all right? So D is positive, f sub xx is negative, and so what that tells me, so positive and negative, it tells me that I have a local maximum at 1 3. So local maximum at 1 comma 3 comma whatever the function is at 1 comma 3. All right, so it's an ordered triple, because we are talking about a coordinate in three-dimensional system. I don't really need you to tell me what the z value is at that location, but you know, people oftentimes can't stop themselves. Like on a test is what I'm saying. So if you write it as 1 comma 3 comma f of 1 comma 3, I'm fine with that, right? That being said, I'm probably going to forget that I said this and then take off credit on a test. You'll just remind me if that ever happens, right? But yeah, it's not bad. It's just stuff. There's a lot of stuff involved. And you'll see as we get, you know, we're working our way through the unit, you see more and more why this unit has to be an open notes unit. All right, so when we take the test, it'll be an open notes test, because like even one sheet of paper, like that's a lot of stuff to write, you know? So just knowing where the information is for this kind of stuff, the second derivative test, it's part of the challenge. Post-its, in the past people have said that they found the most success by just using those like Post-its to identify the relevant pages that had like all the rules and formulas. So this one I think would get a Post-it, you know, so when you're flipping through your pack, because if you've ever taken an open notes test, you know that the big challenge is finding the part of your notes that are relevant to a situation, right? So what you do is you kind of make little tabs for yourself, right? So put a Post-it so that it extends beyond the page a little bit, and just write second derivative test on that Post-it so that you can flip to that page very quickly and easily, right? Instead of being one of those people that's always thumbing through, right? So just a piece of advice. It's probably not anything that I would ever think to do myself. It's just one student, I saw that they were doing it, and I asked, I was like, how did that work out for you? They said it was a lifesaver. You know, like that's how I was able to effectively work my way through the packet. So, you know, just a piece of advice. So we look at our conditions. I already forgot. Negative and positive? Well, I know that the first one was positive. Positive discriminant.
And the double, and the f of x was less than 0.
And it was less than 0, okay.
So local max.
So local max. And then the other one had a discriminant that was negative. So that, take it or leave it, it's up to you. So I'll do one with trig. And I'll leave one for you to try. So find and investigate the critical points. Right, so this is what I was alluding to before, where I was saying sometimes your partials will be in terms of both x and y. All right, so f sub x, hang on to the sign of y as a coefficient, and then take the derivative of the cosine of x, which would be negative sine of x. Then f sub y, hang on to the, because the coefficient really is cosine of x, so hang on to that, take the derivative of sine of y, which is cosine of y. All right. So these need to be equal to 0 and also equal to each other. So negative sine x sine y equals 0, and cosine x cosine y equals 0. All right. So this is an and situation. Normally, I don't bother with the notation when it comes to solving quadratic style situations. I overuse that word. Equations. But here it's very important because the solutions for this have to coincide with the solutions for that. All right. So within each equation, I'm solving for x and y. So I'd write it as the sine of x equals 0, or the sine of y equals 0. Because if either of those are 0, then that first equation zeroes out. Cosine of x equals 0, or cosine of y equals 0. All right, so you've been studying your unit circle. Where is the sine function equal to 0? 0, 180, and so on, right? So 360, and, you know, it maybe go negative 180, you know, dot, dot, dot. All right, same thing would be true for the y. So, or y would be equal to 0, 180, etc. And, all right, so where's cosine equal to 0?
90, 270.
90, 270, etc. Same thing for the y's. Or right? Now, you look at the diagram, and that's why I was saying that I'll give you the diagram, because in the last question, you knew to be on the lookout for one answer. We got our one answer, I was satisfied with that, we moved on. Here, I mean, I see lots of hills and valleys, all right? So that means that there's gonna be a lot, right? And so, infinitely many, in fact. What we wanna do is come up with a rule or set of rules that would define our max and mins, all right? So what I need is any possible pairing of x and y that would make both of these equations equal to 0, all right? So that's the hard part, because that requires the most thought. So x and y. All right, so what you could do is pick out just values of x and y that could make sense. Like, for example, 0, 0. Well, 0, 0 is not going to work, because while it makes this one equal to 0, this one would be equal to 1, because cosine of 0 is equal to 1. So 0, 0 is not an ordered pair. Even though I have a 0 here and a 0 there, it doesn't work for both equations, so that's no good, all right? But if I take a 0 for x, and really anything but these values for y, I'll be in good shape, all right? Because if I take the 0 for x, that's going to zero out my first equation, all right? But it won't zero out my second equation. So then I look to my y's here, the y's that would make this one zero out, because it doesn't matter what y is here, because the fact that x is equal to 0 already zeroes out this whole shebang, all right? So if y is equal to 90, then this is going to be fine, because that's going to make the cosine of y equal to 0, which zeroes out the entire right-hand equation. So 0 and 90 is a possible ordered pair. We could also say 0 to 70. All right, so basically we're at a rule here. It's 0, 90 plus 180k. And we'll define k as belonging to the set of integers, but we'll do that all in one shot, because this isn't our only possibility, all right? So then another possible case would be, okay, well, what if I did the same stuff, but I used a 180 for x? Well, true. So I could say 180, because 180 is going to zero out my first equation, but it won't zero out my second equation if I pair that with a 90, a 270, and so on. All right, so then I would be saying, instead of 0, 90 plus 180k, I'd be saying 180, 90 plus 180k. All right, but if I follow that progression, well, the next one in the list would be 360, and then 540. You know, so would it be 540? Yeah. So then we could generalize that even further by saying, all right, well, these seem to be giving me the set of 180 plus 180k. I'm sorry, 0 plus 180k. I mean, I guess 180 plus 180k would have worked too, but. All right, so instead of writing out every possibility, we came up with a generalization. And then we'll figure out, using our second derivative test, whether this generalization gives us a max or a min. And the good news is, I don't have to use the k's. I just have to use one of my points, all right? And that'll get the job done for me, all right? Because what applies for one of them will apply for all of them, all right? Another case, all right, because I focused on the x values here, but I have a set of y values that would make my sine function equal to 0, all right? But those y values won't make the cosine equation equal to 0, all right? Because that would make it either 1 or -1. So then if I pair these y values with these x values, for example, if I did 90, along with 180 degrees, that would get the job done, right? Because 90 for x would give me something for the x that's not equal to 0, but when I plug in a 180 for the y, that'll zero out, all right? 90 for x, that zeroes out, so I don't even care about what y is there, all right? But basically what we're gonna get at is the reverse, all right? So the roles will be swapped. So another possibility would be, instead of saying 0 plus 180k, we could say 90 plus 180k. And then 0 plus 180k. All right, so now I'll define what k is, where k belongs to the set of integers. All right, so you think back to the last problem. All we did was we took our partials, set them equal to 0, and solved. We got a 1 and a 3. We're done with that in like half of a heartbeat. Here, it took like half an hour, you know, so 10 minutes, I got to count it. But I mean, it's definitely a lengthier process. And we haven't even taken the second derivative yet. We have to do that. My second order partial with respect to, well, it depends on what I'm starting with. So I need second order partials with respect to x, y, and then if I want the mix, I can go x, y, or y, x, because sine and cosine functions are everywhere continuous, so I'm not worried about there being a discrepancy there. All right, so f sub x, x. So hang on to the sine of y. Take the derivative of negative sine x, which is negative cosine of x. All right, f sub y, y. So we're looking at hanging on to the cosine of x, taking the derivative of cosine, which is negative sine of y. So as it turns out, the second order partials are going to be the same. All right, it doesn't always happen, but sometimes it does. Now my second order mixed partial, f sub x, y, is fine. I mean, either way would work. All right, so I'm going to hang on to the negative sine of x and take the derivative of sine of y, which is cosine of y. So I get negative sine x times cosine of y. So the discriminant, d, I could start plugging numbers in, but it's going to get pretty hairy pretty quick. So it's kind of, I don't want to say it's in our best interest, but you know, it seems like maybe doing it in general terms first would be the way to go. All right, so it kind of cleans up nicely. Well, kind of nicely. So, because this is the same as saying negative sine y cosine x. And this is the same thing. So the first part of the discriminant is just multiplying my, my two partials, f sub x and y. So sine squared cosine squared. Sine squared y cosine squared x. minus, now I want the mixed second order partial squared. All right, so minus sine squared cosine squared, right? Sine, but in terms of x and y. All right, so the almost heart attack can subside and you can start to relax, because if the x and y were swapped, this would zero out and it would be inconclusive, which would mean that you would have to use a completely different technique, which would suck because you did all this work, right? So we dodged one there, all right? So what I want to do now is find, because I have two cases really. I want to find my discriminant for the two possible cases. So I'm going to use the 090 because I know that's a good representative of my first scenario. All right, so 090. So I'll find the discriminant at 090. All right, now it is possible it could still zero out, which would be pretty awful also. Rut row. Good. I squared it, right? Oh, okay. Yeah, I'm still having heart attacks here. Right? I thought it was all going to zero out, but I was mentally swapping things in my mind because you see the zero first, and you see the sign first. You're like, that's going to zero out, but it's not because we're putting the 90 in here. So this is going to be a 1. That's going to be a 1. And then this part, we're putting the 0 in for x. That part is going to zero out. So the discriminant at this location is just going to be a 1. Then I do it again, but for 90, 180, for example. I mean, you could do it 90. You could do 90, 0 if you want, but it's all the same. All right, so if I plug in a 180 for y, that's going to zero out. But if I plug it in for x here, it's going to become, I'm sorry, I plug in the 90 for x here, it's going to become a 1. Plug in the 180 for y, it's going to become a negative 1 squared, which is a positive 1. So this whole thing becomes a negative 1. That's the long and short of it. But all those pregnant pauses there were for the purpose of me not screwing this up just by accidentally transposing what goes in for x and what goes in for y. All right, so we have discriminant values. All right. I also need to know what the sign is for my second order partial with respect to x. All right, and I got to do that for these points also. So I'll just kind of jot that off on the side here.
How are we having this quiz?
Like the last 10 minutes. Yeah. All right, so we're popping these values into my second order partial with respect to x. All right, so plugging in a 90 for y is going to give me a negative 1. I'm sorry, positive 1, ultimately negative 1. Plugging in a 0 for x gives me a positive 1, so this ends up being a negative 1 overall. Plugging in a 90 for y. I just wrote this one, 90, 180 is what I wanted. I wrote the same thing, it's the same equation, or same type of point. So 90, 180. Yeah, better. So plugging in a 180 for sine, that's going to zero out. Right. All right. Yeah, it looks good. So, just off on the side here, I'm going to make little notes here. So 0, 90 was for the first type of coordinate, and for that we know that f sub xx is less than 0, and the discriminant is greater than 0. All right. For the second one, f sub xx is equal to 0, and the discriminant is less than 0. This is saddle point. All right. So local max at these locations all right, but the one thing that we seem to be missing would be local mins. All right, so now what we have to do, I mean, it should have actually come up in this process, but clearly I neglected some sort of pairing of values that would have also given 0. But by process of elimination, we've identified the local max. They're going to occur at these points. Local saddle points will occur at these points. If I could just identify the other pairings of x and y that would give me 0 for my first order partials, then I'll know where my local mins would have to be. All right, so we want to consider that. So I did x from this one paired with a y from that one. We did x from this one paired with a y from that one. What am I missing?
I think it's when you combine them, with the k's being the same. Like if you put in k equals 1, you're missing out on a point like 0, 270.
Oh.
So I think it's skipping every other point.
Ah.
So you're gonna have 4 pairings where 2 of them don't work and the other 2, one's a local max, one's local min.
Gotcha. So let me see if I can salvage this. So 0, 90 we did. 0, 270 is the one that would give me a 0, 270. If I plug that in here, yeah, that's the one that would give me positive. Okay, it's a relatively easy fix. So f sub xx of 0, 270 would have given a positive 1, right? And so it's embedded in this whole shebang here. So yeah, there was an overgeneralization, so that's no good. Yeah, so we'll have to break it up into 2 separate categories. So the first, well, actually the first one's fine, right? I just need another one for 270. And so, well, the first one's almost fine. So I'm going to make this 360K. So that it'll skip over every one of the 270s. And then we'll have another one, 180K, 0 plus 180K. Because that part I think was fine. We just need the 270 plus 360K. All right, so for this one, we have f sub xx. Well, this is what we had before, is less than 0, with the discriminant being greater than 0. And this one had f sub xx greater than 0 with the discriminant also being greater than 0, right? So we're talking about local max and local min. All right, so, you know, a little extra stuff in there makes it a little bit more confusing, but absolute extrema, which kind of flows in the same sort of way, except you have particular bounds, all right? So we call f of a comma b the absolute maximum for all values in the domain. We also have f of a comma b being an absolute minimum, and really the notation is just saying that it's higher, that one point is higher than all other points in that domain. All right, this point is lower, physically lower than all the other points in that domain. The extreme value theorem supposes that f of x comma y is continuous on a closed and bounded interval. All right, so real numbers in two space, then then f has both an absolute max and an absolute min in R. All right, so that's the same thing as Calc 1. The way that you handled it in Calc 1 is that you had to not only find any possible critical values that might exist and determine whether or not those were relative extrema, but you also had to test the boundaries of the graph. All right, and so that's where these terms are going to come into play. So it's interesting stuff, but there's a fair amount that goes into it, and it all starts with what we were talking about on the 2 pages ago, and that is the first and second order partials. All right, because we're going to apply the second derivative test. So we're looking at 2x minus 2, and then 2y minus 6. All right, so if I'm not mistaken, this is either the exact same problem that we started with or a slightly varied version of it, but we need to set each of these equal to 0. And solve, and you get x equals 1 and y equals 3. All right, so the first thing I'm going to do with this information is verify that the x of 1 and the y of 3 fall in the restricted domain that was given to me. All right, because it's telling me that my x's have to be between -2 and 2, and my y's have to be between 0 and 4. A good kind of trick question would be, you know, like if I gave you a domain that goes from, the y values go from 0 to 2, that would make this critical point irrelevant. All right, so just be mindful of that. F sub xx is just 2. And my pen is running out of battery, so that's why it looks so crappy. F sub yy is 2. F sub xy, the mixed second order partial, is going to be equal to 0. All right, so no more than 1 0 out of this set of values, and we know that the second derivative test is going to work. All right, so d is going to be equal to, well, we did it already. It's 4. All right, so d is greater than 0. F sub xx also greater than 0. Therefore, we're looking at a local min at 1, 3, f of 1, 3. All right, so just a repeat of what we already did. But we have to go further because it's not the objective of the question to identify local max. Find, of course, I mean, the directions are very similar, but it says find and investigate the critical points of the function on the restricted interval, right? And in fact, that actually kind of, the instructions are actually kind of bad. It should be find the absolute extrema. I really don't know how I've never noticed that typo before. Because the way those instructions were, you could actually walk away being like, that's what it asked me to do, so I'm done. All right, so how do the boundaries come into play? Well, if you're living on any one of these boundaries, it's because you've achieved one of these extremes for x or y, right? So what we need to do is work our way around that square base region and find extreme values for just those boundaries, right? So we're going to decompose this three-dimensional graph into a two-dimensional graph by letting x equal -2 and keep y variable. Let x equal +2 and keep y variable. Let y equal -2, right? We think it's -2. What is it? No, it's 0 and 4. Let y equal 0 and keep x variable. Let y equal 4 and keep x variable. We also have the corners that could come into play here. Right? For those, we could actually just figure out the values. All right? So let x equal -2 and y equal 0. Let x equal -2 and y equal 4. Let x equal +2, y equals 0. And let x equal +2 and y equal 4. And so these are all the things that we have to do that make this problem, well, a bazillion times more complicated, right? But it's really not overly terrible. It's just we have to do a little bit of work, right? So I'm going to let the calculator do as much of the work as possible. But, you know, there's some of it that I'll have to actually do out by hand, right? So there's just not a choice in the matter. So I'm going to let x equal -2 in my function and keep y variable. So that's going to give me f of y, new function f of y. So that's going to become a 4. If I plug in a -2 here, that's also going to become a 4. So 4 plus 4 is 8, plus 14 is going to be 22. So y squared minus 6y plus 22. All right, parabola, wonderful. X equals 2, these are going to zero out, all right, 4 and -4. So y squared, f of y. I think I have to zoom in more. Not that much. Y squared minus 6y plus 14. Now, if y goes to 0, each of my 0 terms are gone, so x squared minus 2x plus 14. So f of x squared minus 2x plus 14. And then my last f of x plugging in a 4 for y's. So 16 minus 24 is negative 10, plus 14 is going to be a positive 4. So x squared minus 2x plus 4. All right, so then I also want to be able to evaluate this function for these particular values, these particular numbers. So that's a little bit of a different story. What I'm going to do is I'm going to store, like I said, I'm going to let the calculator do the work. I'm going to store these values in for x and y, and then just manipulate those. So negative 2, I'm going to store as x, and 0, I'm going to store as y. I mean, it's easy enough to do it by hand, but I just don't want to. So then what I'll do is I'll just type this function in general terms, x squared plus y squared minus 2x minus 6y plus 14. And this is the only time I'll have to type that. So I'll get a 22, because all I'm going to do is I'm going to replace these values. So z equals 22. So I'm going to now store 4 in as y and recompute 14. Absolute extrema, I'm just looking for the biggest z values for absolute max, the smallest z value for absolute min.
Back when you let y equals 4, I think the constant should be plus 6, not plus 4.
Plus 6. Okay. Thank you. Sounds good to me. All right, so 2 and 0, so 2 store x, 0 store y. Recompute. I hate when it does that. I get a 14. So all I have to do is change my y value to a 4 and recompute, and I'll have all these values taken care of, so 6. All right. So again, I'm looking for the biggest z and the smallest z. So these are irrelevant because they're neither the biggest or the smallest. So now what I have to do is find the extreme values for these functions. All right, well, I just made I made a Calc 3 problem into an easy Calc 1 problem. All right, and easy being like I could do this with derivatives, or I could do this on the calculator. Or I could do it by finding the axis of symmetry and vertex. All right, so a lot of different pathways here. Personally, I like to try to take the brain out of it as much as possible. So what I'm going to do is I'm going to type in these functions into my calculator in terms of x. So x squared minus 6x plus 22. All right, there's a function called, in the math menu, function min, function max. All right, so you can handle it that way. If you know that you're on the lookout for a minimum or a maximum, then you just select the appropriate one. Now, based off of what I see here graphically, it looks like it's bellying downward. So if I'm going to find an extreme value here, it looks like they're going to be minimums graphically. Also, these are parabolas that have a positive leading coefficient, so they're upward facing, so that's going to produce a minimum value. All right, so all I would need is to select that f min. Now you plug in whatever the variable or the function in the variable. So alpha y1 is where I stored the function. The variable is x, and then the min and max. Well, the min and max is debatable. But generally, you're looking at something in the negative 10 to 10 range. So, I mean, you could do more with it. I mean, you could graph it if you want, and then investigate, but negative 10 to 10 is a safe bet. So 3 is the x value in this function that gives a minimum. All right, so what I would need to do is plug that into my function itself. So alpha y1, plug in the 3, and see what it gives me. All right, so all I'm finding is the vertex. So the vertex is 3, 13. All right, so this looks like a convoluted approach, but really it's not in the first step that it shows its value. It's in the second step, all right? Because now all I have to do is change my 22 to a 14 and then recompute, all right? So I'm gonna find the minimum again. Turns out it's at the same x value. Well, the a and b values were the same, so it makes sense. Now I get a 5. So vertex is 3, 5. All right. It's the z values that we care about, all right? Because each of these ordered pairs are defined as y, z, all right? Because independent variable is y. F of y, assuming that x is equal to negative 2, it's still f of x comma y. All right, so it's giving a result of z. I'm looking for the largest z value and the smallest z value. So I now know that 6 can't be possibly the largest. I'm sorry, the smallest. All right, I also know that 13 isn't going to cut it either. All right, because I got one bigger than that already. All right, so far my winners are 5 and 22. All right, so go back to my function. Make it a negative 2. Everything else stays put. So 1 is the relevant value. So my vertex here is 113. The z value, depending on the x value of 1, is 13. Well, that's not a winner, so kill it. It's not the biggest. Biggest is 22. It's not the smallest. Smallest so far is 5. All right, so my last possible case would be changing the 14 to a 6. Recompute. Same value for x, and we get a 5. Doesn't matter how many times the 5 occurs. We just need to know what the absolutely lowest value is. So absolute min 5, absolute max 22. The only other thing that I haven't tested, and that's just out of really out of habit, I just always forget, is my critical value. So let me do that real quick. 1, store it in as x, because that actually could be the winner. 3, store it in as y. Very easy to lose that part of the process. Plug it in. That's a 4. Okay, so the absolute min is actually 4. All right, so because this is the coordinate 1, 3, 4. The z value here is smaller than this one and this one. So the absolute min is actually a 4 instead of the 5. All right, so almost screwed that whole problem up.